Hello everyone, welcome to Adam. So now we are going to solve this question based on truss, where we have been asked to calculate like the forces in every beam of the truss. Analyze the truss by the joint method or the section method. So we will be using joint method for this particular problem. So let us see how we can solve this problem. So first of all, whenever you are given problems based on truss, you want to calculate the unknown forces or the unknown reactions in the truss firstly. So first step will be to find the unknown reactions. The second step will be to analyze the truss or the analysis wherever there is a force given or there is a magnitude of force given. Let us say we are using the method of joints here. So whenever you have been given methods of joints, then you want to analyze the truss at every joint wherever there is a force given. So let us say 4 kN force is given 6 or A D is given. So you want to analyze the truss there. So analyze the truss at every joint. At joints where there are, so you want to try the points where there are forces given or magnitude of forces given, like the force 6 and reactions. But if there are less points, then you can also prefer E, where you can find the unknown forces without any magnitude of the force given. But if there are points where magnitude is given, you want to try at that point first. So like analyzing the truss at the joint. So let us see how we can. So what do I mean by analyze is nothing but applying the equilibrium condition at there and finding the unknown forces. So equilibrium conditions, which is nothing but summation of Fy is 0 and summation of Fx is 0. At that every point to find the unknown forces in every beam or a section. So let us just apply these steps in our given problem and try to solve the problem. So firstly, we have a point, we want to find the unknown reactions at A and D. So let us, for that you need to consider the whole truss as a rigid body first. So let us say this is our truss, this is some rigid body. You have this as a 30 and this as 30 degree. Similarly, this as 30 degree and this as 30 degree. You have 4 kilonewton force here and 6 kilonewton force here. You have, let us say this is RA and this is RP. So considering the whole truss as a rigid body, you can just apply the equilibrium condition here. We have a summation of Fy is 0, which means Ra plus Rb should be equal to 10, which is 4 plus 6. Also, you can apply the condition for the torque balance or the condition that summation of moment at any point should be 0. Because there are no horizontal forces here, you do not need to include the Fx condition. So let us just apply the moment condition at point A. We have this 4 kilonewton at a distance of, so this total distance is 9. So this total distance is 9. So the half distance will become 4.5. And we have this as 60 degree, this as 60 degree. So this will also become 60, which means it is an equilateral triangle. So this length should also become 4.5. And this is 60 degree as given. So this length would become 4.5 cos of 60, which is nothing but 2.25. So 4.5 cos of 60, yes, 2.25. So you just need to consider clockwise forces as positive and anti-clockwise as negative for now. They will be following this sign convention throughout the video. So we have 4 kilonewton into 2.25 as the distance between the 4 kilonewton force and the point A in the clockwise direction. So that is why it is positive. And then the second force we have as 6 kilonewton and the distance is 4.5 plus for 2.25. So we have 4.5 plus 2.25, which is 6.75. So we have plus 6 into 6.75. Also, we have this RB force and it is applying an anti-clockwise movement at point A. So it will be RB into total distance is 9. So from this equation, you can calculate the value of RB directly. And the value of RB becomes 5.5 kilonewton from this. So 5.5 kilonewton is equal to RB. And similarly, you can put this into your equation. This is RA plus RB is 10. And you will get that RA is nothing but 4.5 kilonewton. So first step of our question is complete, that we have found out the unknown reactions at RA and RB at point A and point B. So let us just write them, and okay, we have enough space, so it is just let them remain then. We have RA and RB, and then applying the equilibrium condition at every point. We have, let us first try to solve at point A, because we have a force magnitude there, which is 4.5 kilonewton. And as I said, whenever we have magnitude, we will try to solve it there first. And the one assumption here is that you are assuming that all the forces acting on all the internal forces of the beam, like the internal forces are forces that are like not represented in the FBD type, in the total rigid body FBD. Like the 4 kilonewton is an external force, 6 kilonewton is an external force, this RA RB is an external force. So this should be RD. I took it as RB. So let us just make it at D. We have RD. This should be RD. Yeah, everything is RD, not RB. Okay. And as I was saying that the internal forces are the forces in the, like let us say this section AB. So if you section it beam, section this beam somewhere here, then this force is, and then this force inside the beam should be an internal force. So similarly, like this, the every beam of this truss have an internal force, and the force which you see on the body is an external force. So we need to calculate the internal forces in the beam. So we will always take it as a tensile forces. So this is one assumption we are making. So let us write it as assumptions that internal forces are tensile. So this is one assumption we are taking here. And if it comes out to be negative, then we will just know that our assumption was wrong and the force is compressive. So the question will itself tell us that if it is negative, then uh, it should be compressive and not the tensile which we have assumed. So let us solve it further. We have at point A, this is 60 degree, and this is FAE, and this is FAB. And applying the equilibrium condition here, we need to first resolute the force at FAB, or at which we will be doing like this, which is this should be become FAB cos 60, and this should become FAB sin 60. We'll just remove the original force here because we have resoluted. Yeah, and we have 4.5 plus FAB sin 60 is 0, and FAE plus FAB cos 60 as 0. So from the first equation, we have FAB as a minus 4.5 divided by sin 60, which makes the value of AB as a minus 5.19 kilonewton, because we are solving in kilonewton only. 4.5 is in kilonewton, so 5.19 in kilonewton. And the value of FAE can be calculated from the second equation, as FAE is minus FAB cos 60. So, and FAB value is minus 5.19 into cos 60 is 1 by 2. So it becomes 2.595. The value of FAB should be minus 5.19. So minus becomes plus. So it is in the positive 2.595. So we have, let us just write all of the forces that we calculate somewhere here. We have force at AB is minus 5.19 kilonewton. Also, we have FAE as a 2.595 kilonewton. We have RA as 5.5 kilonewton and RB as 4.5 kilonewton. Sorry, this is RB. Sorry, it should be 5.5 for the RD and 4.5 for RA in kilonewton. Let me just write it. It should be clearer. We have a 4.5 kilonewton. We have 5.5 kilonewton. Yeah. And let us now just apply our condition at point B. After we have applied our condition at point A, let us apply our condition at point B. So point B, because we also have a 4 kilonewton force acting at that point. So whenever there is external force, as I said earlier, if you have a known force at any point, try to apply this condition at that point. So you have this point B, you have a vertical force of 4 kilonewton acting downwards. You have this RAB, FAB. Again, we will assume it to be tensile and just put it negative, as we know that IFAB is minus 5.19. So still we will assume it to be tensile at point B and then we'll put it negative when we get our equation. We have FBE and we have BC. Yeah, these are the forces acting at point V. We need to resolve this force into its component, and we have this total angle is 60, so this will become 30 and this will become 30. So we have FBE cos 30 and FBE sin 30. Just remove the original force. We also have FAB sin 30 and FAB cos 30. So these are our resolution of forces. We have all the forces. We can just apply equilibrium condition here. We have 4 in the vertical direction. We have 4 plus FAB cos 30 plus FBE cos 30 as 0. And in the horizontal direction, we have FBC plus FBE sin 30 as FAB sin 30. So if you put the value of FAB in the first equation, you will get the value of FBE. So we have 4. FAB was minus 5.19. Yeah, minus 5.19. So minus 5, sorry, 5.19 into cos 30 plus FBE cos 30 should be 0, which makes FBE as 5.19 cos 30 minus 4. Yeah, 5.19 cos 30 minus 4 divided by cos 30. If you calculate this, you will get it as a 0. Sorry. Yeah, it should be 0.57 kilonewton. So as you can see, it is in the tensile direction. Also, we have our second equation, FBC is equal to FAB sin 30 minus FBE sin 30, which we have calculated in this, like FB you can calculate here and FAB we have already calculated. Then FBC comes out to be minus 2.88 kilonewton. So as you can see, it is coming out to be minus, so it is a compressive force. You can just write the calculated force here again. We have FBE as 0.57 kilonewton. So it should be 0.57 kilonewton. You have FBC as a minus 2.88. So F of BC is a minus 2.88 kilonewton. So let us move ahead. We can apply force equilibrium at equilibrium at point C, because we again have a force at point C, which we know. Yeah, let us try to apply the equilibrium at that point. At point C, we have a 6 kilonewton force acting from upward in the downward direction. We have FBC tensile, CE tensile, and CD tensile. We have BC, FCE, FCD, and this is 30, and this is 30. And FBC is a tensile force, and FBC we have calculated as minus 2.88. So let us just write here, we have already written that's minus 2.88. So let us not write that. We have in the vertical direction, we have a 6 plus FCD cos 30 plus FCE cos 30 is equal to 0. In the horizontal direction, we have FBC. Yeah, we have FBC plus FCE sin 30 is equal to FCD sin 30. So if you know FBC, but you know FCE and CD, so from the second equation, you have tried to substitute one of this like terms from the other term. Like let us substitute CD. So we have F CD as a minus F C E. Yeah, FCE cos 30 minus 6 divided by cos 30. If you put it in the second equation, you have FBC plus FCE sin 30 is equal to minus FCE cos 30 minus 6 divided by cos 30. So you have FBC cos 30 plus FCE sin 30 cos 30 is equal to minus FCE cos 30 minus 6. And if you put your value of FBC, which is a minus 2.88 as we have calculated earlier, so it will, like, you can just divide this equation also by cos 30. It will become more easy. Let us just do that. We have FBC, so dividing by cos 30, we have FBC, which for which the value is minus 2.88. We have calculated earlier. We have minus 2.88 plus FCE sin 30 plus FCE is equal to minus 6 by cos 30. So FCE will be 1 plus sin 30 is equal to minus 6 by cos 30 plus 2.88. So if you calculate this, we have minus 6 divided by cos 30 plus 2.88 divided by 1 plus sin 30. We have minus 2.69. So minus 2.69 becomes our FCE. You can put this FCE value into this equation and you will get the value of, let us say, FCD, which will be 2.69 into cos 30 minus 6 divided by cos 30. You will get is minus 4.2 kilonewton. So you got FCD and FCE. So let us just write it here. You have got FCE as minus 2.69, FCD as minus 4.2. kilonewton. And we can now solve this further. So okay, so we only want the value for CED now because we have all the other forces. So let us see how we can calculate the value of ED also. We have a equation at point E. So let us apply at the point E now. We have these two forces and we have these two forces 60 degree, so BE and CE. So we have BE, CE, we have FAE and FED. So this is 60, this is also 60. We can just apply the equilibrium condition, which is CE cos 60 plus FED is equal to BE cos 60 plus FAE, and CE sin 60 plus BE sin 60 is equal to 0. And you know the value of like BE and CE from your previous calculation. Yeah, you know BE as 0.57 and you know CE as minus 2.69. So you can just so BE should be equal to CE from this equation. Okay, so the value of CE sin 60 should be equal to BE sin 60, which means that BE should be BE should be equal to minus CE, and we have already calculated BE, which is 0.57. So CE should become minus 0.57. We need to update our values. So this value is not correct. Like the whatever we did at point C should not be there. Let's just rub this. Yeah, we have CE as minus 0.57, and if you put CE and BE at this like equation, which is the first equation which we have, like this equation, then you will get, you have the value of FAE also, like FAE from the above you will get as 2.595. Then you can directly get the value of FAD. FAD will come out to be something as 2.02 and minus 2.02, sorry. So yeah, FAD should be this, and FB, you know, FCED, you know, and AE also, you know. So let us just update our values. FCE should be minus 0.57. So FCE it should be minus 0.57. And we have also calculated now FED, which was minus 2.02. We need a FCD now, which we will calculate. At you can also calculate this at point C or point D. So let us just calculate at point D because we have all the values there also. And yeah, let us calculate it at point D. At point D, we have a force. Let us assume it to be tensile again. And we also have, let us call it FDC. We have FDE. And we have 5.5 kilonewton force acting in the downward direction. This should be 60. So for the equilibrium condition, we have 5.5 plus FDC sin 60 should be 0. Also second is the horizontal correction. We have FDC cos 60 plus FDE should be 0. So we have the value of FDE from the like above calculation as minus 2.02. So okay. So let us just check our value. So we have DC as a minus 5.5 divided by sin 60. So minus 5.5 divided by sin 60 will give you minus 5.5 divided by sin 60 will give 6.35. That should not be, yeah, so value of CD should become 6.35 in the negative direction from this equation right here. So yeah, you can use this equation to find FCD. So we have found out all the forces in the truss. So this is how you can solve this question. Thank you.